All right, Math 99. We're starting on page 299. I'm mailing today your little blue card is what I call it. It's a blue laminated card with many formulas and facts. It's just a nice recap of notes that you can keep in one place with respect to moving into 090, 0100 and beyond. So you might want to send your U.S. postal mailing address to me if you have not. Otherwise, those of you that did, I've mailed your cards today. Okay, example 7 on page 299 in section 4.5. We've been working with polynomials in addition. We might add a monomial to a binomial plus a trinomial or a polynomial. So we're looking at our terminology and manipulating with addition, subtraction, and now we've been experimenting with multiplication. So today we're continuing with multiplication, and we have a binomial times a binomial. Four x plus 3 times a quantity, x minus 2. And share. So a binomial times a binomial, 4x plus 3 times x minus 2. Well, we're going to have a plan as to how to multiply. And our plan is to multiply the first binomial's term times every term in the second binomial. So it's distribution of every term in the first polynomial times every term in the second polynomial. So 4x times x would be 4x squared. This is subtraction. I'm going to change to addition and add the opposite so I get my sign under control. And now 4x times a negative 2 would be a negative 8x. I need to multiply every term in the first binomial times every term in the second binomial. So 3x, or 3 times x would be 3x. And distribute 3 times the next term, and that'd be a negative 6. When we're multiplying polynomials, we always check to see if we can collect like terms. Because we've expanded this, there may be some like terms. So any more x squared terms? No. This was a negative 8, wasn't it? 4x times a negative 2 for a negative 8x. X to the first degree, I have a negative 8x plus a positive 3x would be a negative 5x. Plus, that's my only constant term, a negative 6. And then arrange your final answer to a little bit cleaner. 4x squared. This is plus the opposite, so we can remove the sign and change back to subtraction. Same thing here, plus the opposite, remove the sign, change back to subtraction. So 4x squared minus 5x minus 6. Our next example, we have x plus 4, the quantity, times x squared plus 2x minus 3. We're multiplying polynomials. Actually, this is a binomial times a trinomial. And once again, we need to take the first term of the first polynomial times every term in the second polynomial. The next term in the first polynomial times every term in the second polynomial. So it's distribution of every term in the first polynomial times every term in the second polynomial. So I have x squared times x squared would be x to the 4th. Pick up your sign. X squared times the next term would be 2x cubed. Pick up your sign and multiply x squared times 3. That'd be 3x squared. Next term in the first polynomial is 4. I get 4x squared. Pick up your sign. Distribute 4 times 2x would be 8x. Pick up your sign and multiply 4 times 3, which is 12. Now, I didn't change subtraction to addition and add the opposite in that case. I just picked up the sign of subtraction, and then I'm multiplying times the term itself. I handled it by just picking up the operation of subtraction. Now, whenever we are expanding in multiplication polynomials, we look to collect like terms. So x to the 4th. There are no other x to the 4th terms. X cubed. There are no other x cubed terms. X squared terms. I have a subtraction. I'm going to change that to addition and add the opposite so I know the sign of my term. I have a negative 3x squared plus 4x squared, which will be a positive x squared. Next is x to the 1st degree. There are no other x to the 1st degrees, and my constant. X to the 4th plus 2x cubed plus x squared plus x minus 12. Two x squared plus 3x minus 4 times the quantity 2x squared minus x plus 3. Let's arrange to take care of subtraction right away. So change subtraction to addition and add the opposite. Change subtraction to addition and add the opposite. Then I do have control of my signs. This is distribution of a trinomial times a trinomial. So my plan is to distribute every term of the first trinomial times every term of the second trinomial, and then collect like terms. So 2x squared times 2x squared be 4x to the 4th. Pick up your sign plus 2x squared times a negative x. It's going to be a negative 2x cubed. 2x squared times 3 is going to be a positive 6x squared. Plus, I have 3x times 2x squared. 3x times 2x squared is going to be 6x cubed. I'm columnizing. might be another way that works a little easier for you. 3x times a negative x would be a negative 3x squared. And 3x times 3 is going to be plus 9x. And distribute my last term. Negative 4 times 2x squared is going to be a negative 8x squared. Negative 4 times a 2x squared be negative 8x squared. A negative 4 times a negative x is going to be a negative 4x. Positive 4x. So negative 4 times a negative x be positive 4x. And a negative 4 times 3, negative 12. Now we're going to collect like terms. For x to the 4th. I have 6x cubed, subtract 2x cubed. I'll get a positive 4x cubed. Here's a negative 11x squared plus 6. Negative 11x squared plus 6 would be a negative 5x squared. 4x plus 9x be positive 13x. And I have just the constant. I'm going to subtract 12. 4x to the 4th plus 4x cubed minus 5x squared plus 13x minus 12. Another trinomial times a trinomial. Three x squared minus 2x minus 5 times the quantity, 2x squared plus x minus 2. So I know that I'm going to use distribution to distribute every term of the first polynomial times every term of the second polynomial. I have some subtraction going on, so let's arrange to change subtraction to addition and add the opposite. Now I know the sign of my terms, so I can multiply. So 3x squared times the first term would be 6x to the 4th. 3x squared times the next term is going to be 3x cubed. Pick up your sign, and 3x squared times a negative 2 would be a negative 6x squared. I'm going to columnize again. I have more terms to manage. It seems to be a little neater to columnize. My next term is a negative 2x. A negative 2x times 2x squared is going to be a negative 4x cubed. A negative 2x times x is going to be a negative 2x squared. And distributing, a negative 2x times a negative 2 will be a positive 4x. And distribute my last term times every term in the second polynomial. A negative 5 times 2x squared will be a negative 10x squared. A negative 5 times x is going to be a negative 5x. And a negative 5 times a negative 2 is going to be a negative 10. And now I can add to collect like terms. Six x to the 4th minus x cubed minus 18x squared minus x. And this is a negative 5 times a negative 2 would be a positive 10. My last term is negative 5 times a negative 2 for a positive 10. Okay, we're supposed to graph, so we'll use GeoGebra. We're supposed to graph y equals 5 minus x squared. Okay, so in my input bar, I'm going to type y equals 5 minus x squared. And I get a parabola, is what this curve is called. And I'm supposed to find what is the approximate value of y when x equals negative 1. Well, when x equals negative 1, I can see visually when x is negative 1, I want to go up and maybe it's around 4, 3.99, 4.1, right in there. Looks like that's where I'm going to intersect with my curve. So let's try letting x equal negative 1. So in my input bar, I'm going to type x equals negative 1. Now I'm interested in that exact point where these two objects intersect. So I'm going to pull down my point button to intersect. And I want to intersect, I'm pointing and clicking on this object and this object. And it will create for me a point labeled. And in the algebra window, I see that I have my parabola, y equals x, negative x squared minus 5. I have x equals 1, my vertical line, and I have point A labeled as negative 1, 4. So when x is negative 1, my intersection point is the point negative 1, 4. So we're able to solve that graphically. Let's look at it algebraically. I want to solve when x equals negative 1. So for every occurrence of x, I'm going to carefully substitute negative 1. Copy everything else down the same. Exponents, the base, I have a clue, I have a negative base. That's negative 1 times itself twice for positive 1. And y equals 5 minus 1 is 4. So when x is negative 1, y equals 4. So our Cartesian plane point is x is negative 1, y is 4. And in this example at MyMathLab, it's offering you a multiple choice response. The next example at MyMathLab is the number n in millions of hearing impaired individuals of age x can be approximated by, and we have a polynomial, n equals negative 0.00006x cubed plus 0.006x squared minus 0.1 times x to the first degree plus 1.7. So we have this polynomial that we're working with, and maybe we'd like to solve it algebraically, then try to substitute, solve graphically rather than algebraically. So let's use GeoGebra. So in my input bar, I'm carefully going to type. Remember, we need to transpose to x and y. So n is going to be y equals negative 0.00006x cubed, use your caret symbol, plus 0.006 times x squared, use your caret symbol, minus 0.1 times x plus 1.7. And doesn't like my formula. So I'm going to try again. Y equals negative 0.0006 x cubed plus 0.006 x squared minus 0.x to the first degree plus 1.7. Okay, negative 0.0006 times x cubed plus 0.006 times x squared minus x to the first degree, and it's minus 0.1 times x to the first degree plus 1.7. I am having troubles with this entry into GeoGebra. Y equals negative 0.000 times 6x cubed plus 0.00 times 6x squared minus 0.1x plus 1.7. And I'm going to have to come back for you and show you how to enter this because I'm having difficulty entering this into GeoGebra. So we'll come back to this one. It should be a parabola opening down, and I'm just not getting it entered correctly for you to see. So it should graph to a parabola opening down. We have our age as the horizontal axis, and we have our Y as the number of individuals graphed at that age. So we want to find out by letting X equal 45 and 55. I'm going to try one more time at GeoGebra. I've got my points plotted here. I solved it algebraically, but let's try one more time with GeoGebra. All right, so I'm converting to X and Y. So Y equals negative 0.1234 6x cubed, use your caret symbol, plus 0.006 times x squared. We're going to subtract 0.1 times x plus 1.7 and enter. So I'm going to do a right click to get the objects property, setting my X and Y min. I'll set my X min to 0 and my Y min to 45. And my Y min to 0 and my Y max to 6. And it's set to 9. So I did a right click so I could set my properties. You see the little gear button. And then I'm looking at preferences for graphics. I'm trying to hone in on my X and Y values between 0 through maybe 85, 90 with my X and Y, my X min and max, X min, Y max. And my Y values, they're in the first quadrant, so 0 through, looks like maybe 6 was our top value at that point. So we are looking at what is approximate to the nearest million, the number of hearing impaired individuals of ages 45. Remember, X is acting as our age horizontal axis. So when X is 45, we're right up here to maybe 4, maybe not quite 4. So let's let X equal 45. For hearing impaired individuals age 45, does intersect with our parabola, or with our polynomial. Let's find out where it intersects. And the point is labeled for us. The point of intersection is, looking in our algebra window, let's make that a little wider, the point 45 for x, y is 3.88. So not quite 4. That's kind of what we were guessing from the graph. And then at my math lab, they ask us to solve the number of millions of individuals at age 45 who are hearing impaired, but the directions continue to state round to the nearest million as needed. Well, we're at the point 45, 3.88. So rounding to the nearest millions would be 4. We're going to round up to the nearest millions. It's 5 or greater, so we're going to round up. So our answer is 4. So using GeoGebra to graph and hone in on a particular area, or you could have solved this by substituting 45 in for x and solved it algebraically. Well, then we begin to look at special products. Well, product means our answer when we multiply. So we're looking at special cases when we multiply, particularly polynomials. And we're looking at these special products when we have a binomial times a binomial. So we might have the binomial x plus 3 times x minus 5. Now we know that we're going to multiply every term of the first polynomial times every term of the second polynomial, but we have a little shortcut that we can use when we have a binomial times a binomial. We call it FOIL. We're going to multiply the first terms, get x squared. We're going to multiply the outer terms. It's going to be a negative 5x. We're going to multiply the inner terms, be plus 3x. And finally, we're going to multiply the last terms. So FOIL stands for first, outer, inner, last. So it's one of those helpful, kind of silly mnemonic reminders that when we have a binomial times a binomial, we can use FOIL. Maybe you can think of FOIL as 4 terms, 1, 2, 3, 4. We have 1, 2, 3, 4 terms. Special product rules for multiplication of a binomial times a binomial. Now, FOIL works for a binomial times a binomial. Otherwise, we're going back to our longhand distribution of every term in the first polynomial times every term in the second polynomial. Well, we've expanded, so then we look to collect like terms. So x squared, x terms, 3x plus a negative 5x would be a negative 2x. And there's my constant. So x squared minus 2x minus 15. Special product rules for a binomial times a binomial. Okay, I want to recognize that I have a binomial times a binomial. So I'm going to use FOIL. Multiply the first terms, multiply the outer terms, multiply the inner terms, multiply the last terms, and then collect like terms. So multiplying the first terms, I have x times x squared would be x cubed. Pick up my sign. X times 5 is 5x for the outer terms. My inner term is 8 times x squared. And my last term, pick up your sign. 8 times 5 is 40. So I've expanded using FOIL as a hint or tip when I'm multiplying a special case of a binomial times a binomial. And now, once expanded, I need to collect like terms if possible. X cubed is x cubed. X squared, x, and my constant. X cubed plus 8x squared minus 5x minus 40, with no like terms in this case to collect. X plus 7 times the quantity x plus 4. Again, it's a binomial times a binomial, so I'm going to use FOIL. X times x would be x squared plus 4x. Inner terms plus 7x. My last terms plus 28. Look to collect like terms. I get x squared plus 11x plus 28. Y minus 3 times the quantity y minus 2. I have a binomial times a binomial. That's what I want to establish first. So I have a special product rule for binomials. I'm going to use FOIL. First terms, dy squared. Pick up your sign. Outer terms, 2y. Inner terms, pick up my sign, 3y. And last terms, it's a negative 3 times a negative 2 for a positive 6. Now I'm going to collect like terms. Y squared, a negative 2y plus a negative 3y would be a negative 5y plus 6. Y squared minus 5y plus 6. Skipping a couple steps with changing subtraction to addition. If you want to do that, you surely can, and I probably will again, on and off. If you're not sure, always change subtraction to addition and add the opposite, so you are controlling the signs as you're multiplying with using real numbers. Be sure to check the overview document at D2L, where all assignments and details along with due dates are mentioned in my daily journal with you. Certainly you should have MyMathLab established with your profile and personal account by this time, and be working on self-study along with Chapter 4 homework at MyMathLab. Thank you very much.